Section 33.7, the mean free path. Let's look at this gas. We have a bunch of gas particles. This particle is moving towards this direction. Over here, collision occurs. This particle changes its direction until it collides again, changes direction, collides, changes direction, another collision, another collision. So the number of collisions experienced by this particle is approximately equal to the number of segments. So one segment, one collision, two segments, two collisions, three collisions, four collisions, five collisions, six collisions, seven, eight. Eight collisions, eight segments. We can calculate the average distance this particle travels between two successive collisions. How? Very simple. If we know the total distance traveled by this particle and then divided by the number of collisions, that's the average distance between two successive collisions. And that's called the mean free path. The mean free path, denoted by lambda, is defined as the average distance a gas particle travels between successive collisions. All right? And by comparing these two pictures, you understand if we have a denser gas, there's going to be more collisions, and these segments are shorter. You have a smaller mean free path. Well, if you have only one gas particle in the container, of course, the mean free path is infinity. It's not going to collide with any other particles. Now imagine in a room you have only two gas particles. How long does it take for these two particles, two small, tiny molecules, to collide with each other? I don't know. It's going to take a very long time, and during this very long time, these two particles can travel a very, very long distance. Now let's look at the formula. Lambda is simply the distance traveled by the particle in a time interval delta t. So this is distance traveled, and divided by the number of collisions. Again, both are in the same time interval delta t. Therefore, this delta t and this delta t eventually will cancel. How do we calculate the distance traveled? Very simple. The speed of this molecule times delta t. The number of frequency, simple. The collisional frequency times delta t. Again, delta t and delta t cancel. You have v1 on top. On the bottom, you have z11, lowercase z11. So this is the collisional frequency of one individual atom of type 1, right here. All right. Supposedly, this should be n sub 1, minus 1, because this particle does not collide to itself. It only collides with the other n1 minus 1 molecules. But usually we deal with a very large number of molecules. So n1 minus 1 is simply n1, right here. And then this v11 is v1 times the square root of 2. Why? v11 is the relative speed. And here is the formula. Type 1 particle collides with another type 1 particle. The relative speed is the square root of 2 times v1. So these two partially cancel. We have a square root of 2 on the bottom. And then this n1 over v. This is the number density. This is the number of type 1 atoms or molecules in this volume v. And we can rewrite this n1 as a product of the Avogadro constant and the number of moles. Why do we do this? Well, n over v is simply p over RT. That's why. So we can express this in terms of pressure and temperature. And usually it's easy to measure the temperature and pressure. So we have this equation for the mean free path. And also we realize this R over N sub A is simply the Boltzmann constant. Therefore, this can also be used to calculate the mean free path of a gas particle. Again, this K sub B is the Boltzmann constant. It's roughly 1.38 times 10 to the power of negative 23 joule per Kelvin. We can tell this lambda depends on temperature and pressure. If you have a higher temperature, you have a lower number density, and then you have a longer lambda. When the pressure is high, you have a higher number density, and then therefore you have a lower lambda. At the room temperature and 1 atm, we can calculate this mean free path for the argon atoms. We're using this equation, we're plugging all the numbers. All right, so this is the pressure, and this is the collisional cross-section area. Where did I get this number? Well, from this table. Collisional parameters for various gases. So we have different gases, we have their radius, we have this collisional cross-section area. So if we look at argon, the cross-sectional area is 0.36 square nanometers. 0.36. And I converted this 1 square nanometer to 10 to the power of negative 18 square meters. Do the calculation, you'll get 80 nanometers. So on average, an argon atom will have to travel 80 nanometers between two successive collisions. The average speed of an argon atom is roughly 400 meters per second using this formula. Okay, this is the average speed. And then we can calculate the time interval easily. The collisions one argon atom experiences every 80 nanometers. So this is the distance it travels between two successive collisions. This is the speed of that argon atom. And then by doing this division, we get 0.2 nanoseconds. Right? So it takes only 0.2 nanosecond for that argon atom to travel the average distance between two successive collisions. All right? So it's pretty fast. Every 0.2 nanosecond there's a collision. So on average, each argon atom experiences 5 billion collisions every second on average. 5 billion. Again, this is a table for the radius and collisional cross-sectional area over here. CO2 is a linear molecule, right? O2, N2, they are linear molecules. They are not spherical. So these numbers are just an estimate. Where imagine these linear molecules are rotating, and then if they rotate really fast, and they do rotate really fast, we just imagine a sphere of those fast rotating molecules.